All right, let's do some practice problems using the ideas of colligative properties to see if we can't find out the molar mass of certain components. One particularly useful way of using freezing point depression is to use an organic compound called camphor. It's it's very smelly. If you think of like a medicine smell, camphor definitely would fit that type of bill there. It's particularly useful for this type of experiment because it has a very large cryoscopic constant of 40 degrees Celsius per molal, meaning that it's very easy to see a temperature change even when we are using just small amounts of substance added to our camphor. Camphor originally melts at 179.8 degrees Celsius. And so if we take 0.186 grams of an organic compound and we add that to 22.01 grams of camphor, we find that the new freezing point is 176.7 degrees Celsius. Let's see if we can't use this information to determine the molecular weight or molar mass of the solute, of this mystery organic compound. And so this would be a good place, if you're comfortable, go ahead, pause the video, and resume it when you're ready to see the answer and the work. In the meantime, we'll go ahead and solve it, or I'll go ahead and solve it, and you can follow along and see if you've got it right or if you just need the guidance on this first problem. So this is given to us as a freezing point depression problem. So we would want to remember our formula. We have Kf, I, and the molality of the solution. We have Kf, we have I, because this is an organic compound, and we also have an organic solvent, a solvent that isn't water, so I is 1. And the molality we don't have. We do have our freezing point depression. We know our pure solvent freezing point. We know our new freezing point. So we can find delta TF. So the only point that's missing here is the molality. And we'll be able to solve for that and then see if we can't work with that further. So delta TF, as we remember, is our kind of final minus initial, or our original freezing point, which will be negative Kf times I times squiggly m. So we have 176.7 minus 179.8 be equal to negative 40. I'm going to just plug in all our values here, times 1 times the molality. Doing so, let's see if I can't do this math in my head, 2.9, negative 2.9 degrees Celsius. Yes, equals negative 40 times the molality. So the molality, oops, I forgot we have the degrees Celsius. We'll just, the degrees Celsius will be the same on both sides, so that'll cancel out. Our units of molality will also cancel out, so let's just not worry about the units right now. Times the molality. We technically have to put the units of molality here. I understand it's weird to have the variable as well as here. We can replace one of them with x. X molal, and therefore the units will cancel out. So if we do the calculation, negative 2.9 divided by negative 40, our molality is 0.0725 with 2 sig figs. That's, as we know, moles per kilogram. That's our molality here. And so we can use this now to determine the molar mass. If you remember, we have in our problem our mass of solvent, which means we can put that in the kilogram spot, so we can see how many moles we have in the solution overall. So that's how many moles in 1 kilogram. But we don't have 1 kilogram, do we? We have 22.01 grams. So if we multiply this number, I guess we'll need to put it into kilograms. Was it 22.01? Yep. So kilograms will cancel. We'll be left with moles. So that number times 0.02201 gives us 0.00159557. Still 2 sig figs here. And now, this is how many moles of solute. We know we have 0.189 grams solute. If you remember how to figure out molar mass, just look at the units, grams per mole. And so the molar mass of this, or molecular weight, whichever one you want to use, will be 0.189 grams divided by 0.001597 moles. And so if we just do this, 0.189 divided by our answer, we get 118.4 or 120 grams per mole with our appropriate sig figs. And that's a reasonable number, right? Molecular weights have to be bigger than 1, because that would be a single hydrogen atom. And for most organic compounds, they're, within 1 to 500. And again, really 1 is not really very useful because that's a hydrogen atom. So really maybe like 20 to 500 is pretty reasonable for a molar mass of a regular organic compound. We'll see in the next problem that we may end up with something higher because we're dealing with a much more complicated molecule. But that's how we're going to find molar mass here. You solve for moles, you have grams experimentally, and grams divided by moles will be your molar mass. And so you can just go ahead and do the calculation. Let's look at another one. So let me move down just a little bit so my face isn't in the way. We have 3.5 milligrams of a protein is dissolved in 5 mils of water, or to make 5 mils of water solution. If we assume the protein is a non-electrolyte, we can calculate the molecular weight of the protein if the osmotic pressure at 25 degrees Celsius is 1.54 torr. Again, I would recommend pause the video, try and solve it, and then resume the video and see if you've done everything correctly. So let's take a look at our formula here. We know osmotic pressure is I times MRT. We have a non-electrolyte, which means I equals 1. Molar mass we don't know. R we do know, 0.08206, though that's atmospheres, so we're going to have to change our osmotic pressure in the right units. And we have a temperature as well. We just need to get that in the right units. So let's go ahead and get both of those into the right units before we go ahead and solve for our molarity. Just like before, we're going to want to solve for moles and use that moles with our given mass to start, and we'll go from there. So we need 1.54 torr in atmospheres. Again, the reason we need that is because R has units of atmospheres. Remember that it's 760 torr for 1 atmosphere. And then we also needed our degrees Celsius. Hopefully we know that's 298 Kelvin, most common temperature we use, right? So should not be too bad. So 1.54 divided by 760 is 0.0020263,158. We need 3 sig figs here, so we'll keep that in mind. The atmospheres. All right, so with this in mind, we can say, aha, now we can plug in some numbers. We have 0.0020263. I'm just going to leave it there. Atmospheres, that's our osmotic pressure, is equal to 1 times our molarity times 0.08206 liters, atmospheres, Kelvin, mole, times 298 Kelvin. So we know atmospheres will cancel, kelvins will cancel. We're left with liters of moles times moles per liters, which is what we should get, right? So if we divide everything across, so take our original osmotic pressure, divide that by 0.08206, divide that by 298, we end up with our molarity equal to 8.286 times 10 to the negative 5. With this, it looks like we're going to still have 3 sig figs. That's moles per liter. And so, we want to think, how are we going to get moles so that we can figure out molar mass? We have to remember, in our original problem, we did have a volume, right? We had 5 mils. So we can figure out the moles. That's how many moles in 1 liter. So how many moles in 0.05 liters? 0.005 liters. Well, that'll be, let's find out, 0.005. We have 4.143 times 10 to the negative 7 moles. We have our original mass, which is 3.5 milligrams. So our molecular weight, or molar mass, will be our grams. So 3.5 milligrams, or 0.0035 grams, divided by this molar mass. Notice we're going to get a very big number this time, because proteins tend to be pretty large. So that's pretty standard. So let's go ahead and do this. 0.0035 divided by our previous answer gives us 8,447.7, which we will round to 3 sig figs, 8,480 grams per mole. So it's actually a pretty small protein. 8 kilodalton, that's not very big. But proteins, you're expecting them to be of larger molar mass, because proteins, as we know from biology, are many hundreds of units long. Each of those units is at least about 50 grams per mole at least. So hundreds of those, it totally makes sense that we'll get something about 8,000 grams per mole. And so there are ones that have millions of grams per mole, so thousands is not a problem there. So again, very important thing to note is that our number is greater than 1. That's the absolute minimum. You cannot have a molar mass less than 1. So always think about, is your answer reasonable or not? And so it's a good idea to have these kind of rough ideas of how big molecules can get. So using organics, you don't really go above 500 very often. For ionic compounds, again, you're looking maybe about 500 is probably the upper limit, depending, unless you're using very, very heavy elements like uranium and a bunch of phosphates or something. Then it can go a little bigger. In proteins, we can totally go way, way longer. Okay, so with that, we are good to go, and we'll see you in our next video where we'll discuss colloids.